Hello friends, welcome back to Tech Easy YouTube channel. Friends, this will be the Kubernetes Mastery Series Zero to Hero episode 5. Here we will go deep into the Kubernetes networking stack. Okay, so without wasting time, let's start with our video. So here this is the episode 5 of Kubernetes Zero to Hero course that we are uploading on YouTube. Okay, so here let's start with the core networking requirement of Kubernetes. Let's discuss what is the requirement of Kubernetes networking. Okay, so there are basically three hard rules that Kubernetes imposes on any network provider. Basically, Kubernetes uses the plugins, third-party plugins for providing the networking stack, okay, or to enable networking inside the pods and nodes. Okay, so here it means Kubernetes has imposed the three mainly standard rules. Like for pod to pod connectivity, there is a rule like every pod can communicate with every other pod without net. Okay, what is net? Network, if you don't know, then you can see my previous video. It's basically a network address translation. Okay, so and second rule is node to pod connectivity. Every node can communicate with every pod without net. Okay, and as self-identification rules, the IP a pod sees itself as is the same IP others see it as. Okay, so here let's understand why these rules exist. Basically, first rule is pod to pod connectivity. Like all pods talk to each other directly. Okay, why it exists? Because here Kubernetes want to simplify app development, so no port mapping needed. It means it's minimizing the developers overhead and also the administrators. Okay, so for node to pod rule, like the host can talk to the guest pods. Okay, so main objective is this, like host can talk to guest pod. Okay, so allows the system to manage and monitor the pods. Okay, so third one is the self ID. Like here it's like I am who I say I am. Okay, but it means it's really truth that I am telling to me is the actual truth. I am telling to others also. Okay, same, there is no difference in my ID. Okay, so it basically prevents networking confusion in distributed system. Okay, so let's move further here. So let's understand the CNI, container network interface. This is the most important thing you have to understand about Kubernetes networking. Okay, so if you understand the CNI, then you mostly understand the Kubernetes networking. Okay, so Kubernetes does not actually do the networking, it delegates it to the CNI plugin. So who developed the CNI plugin? There are multiple providers for the CNI plugin like Planet, Salico, Cilium, Weave, etc. Okay, so as per your different requirement, you are going to use the different CNI plugins. Okay, so all plugin are not set or fit for all the requirements. You have to brainstorm within your team what is your actual requirement, what you want to achieve. Based on that, you can choose the CNI plugin. Okay, so like the flow is like that. Like basically what is CNI? A standardized specification for configuring network interface in Linux containers, and it should follow the three basic rules that we discussed here. Okay, so the flow would look like Kubernetes calls the CNI plugin when a pod is scheduled. When we already discussed the pod lifecycle, like what are the four important pod lifecycle was there? Like first was the printing state, and second one was ready and running, and there is a failed state also, and also there was undetermined state. Okay, so here when a pod is scheduled, then Kubernetes basically called the CNI plugin. CNI allocates an IP address by using the IPAM. Okay, so CNI creates a virtual Ethernet pair to connect the pod to the node. Okay, it means one side of virtual interface will be created inside the pod and one side will be attached to the node. Okay, so we will go into deep. Okay, for now just you can understand the one side of wire will be inside the, if you think like a virtual Ethernet is a wire, then one side will be inside the pod and one side will be plugged inside the node. I hope you are understanding. Okay, so common providers, as I already discussed, Flannel, Calico, Cilium, Wave, and also others CNI plugin developers are also, but these are the common. So first let's understand the pod-to-pod communication within the same node. So when pod A talks to pod B on the same node, the traffic never leaves the physical host or virtual Ethernet. You can say. Okay, so bridge mode, most CNI create a virtual bridge like CNI 0. Then path will be pod A to veth pair and then CNI bridge, then veth pair of pod B, and then it's go to pod B side of interface. Okay, but here sometimes some providers can also uses the routing based method. So there they will maintain basically dynamic routes inside the host namespace there. Okay, that will be managed by the CNI, and then they can route the traffic. Okay, so this is the for the same. So they can also use those based, but for pod it will be not going to change. For the same node, communication will happen in this manner only. But key concept is this is just a standard layer 2 switching behavior within the Linux kernel. Okay, so here CNI bridge is the everything. Okay, that manages the basically routing and switching both. So pod-to-pod communication across node. So when we have a pod in then traffic, when we have to communicate, like pod A want to communicate from pod B that is in different host, okay, or different node you can say, then traffic must cross the wire. The CNI must route it to with the two primary method. First one is encapsulation, that is the overlay. Okay, wrapping the pod packets inside a node to node packet, like by using VXLAN or Geneva. It's very good for restricted network. And second one is the direct routing by using the underlay, like by using the BGP or static routes to tell the physical network where pod IP is live. Okay, live. That is basically used in the high performance mode where we want high performance within our cluster. So let's understand the service abstraction. So we know that pods are ephemeral in nature, they die. So when they die, their IP is also going to change. So basically services provide a stable entry point. Okay, like they provide this cluster IP, the default virtual IP reachable only inside the cluster. Basically how it works, it is not the real interface, it exists as a logic inside the kube-proxy. Okay, so basically kube-proxy imposes everything or inject inside the host kernel. Okay, so basically here all the magic is happened by the kube-proxy. Basically kube-proxy is the brain on every node that manages service routing. It typically operates in IP table mode. Okay, so DNAT is used like destination network address translation. When a packet hits the cluster IP tables intercepts it and replace the destination with a random ready pod IP. Okay, so kube-proxy directly communicate with the API servers like from controller node itself, and also as per the direction received from the controller, it's basically injects the changes inside the host kernel, or you can say node kernel. So the downside is the IP table is sequential list. In massive cluster like where we have to run the 5000 plus services and pods, performance may degrade. Okay, so how kube-proxy works basically in the IP table mode. So it's basically a work like a watcher, okay? Like it's a take instruction from control plane. Basically, it syncs from control plane. You can understand that. So action like kube-proxy maintains a constant watch on Kubernetes API server. Okay, that sits inside the control plane. Okay, master. You can say on master node. So it's trigger when a new service is created or a pod passes its readiness check. Okay, so now results is like kube-proxy dynamically injects updates iptables rules directly into the node's Linux kernel. Okay, so here you have to think that like every node has a kernel. Okay, so mostly Linux kernel. So Linux kube-proxy very closely work with the Linux kernel, and it's basically inject everything that is received from the kube API server, every instruction. Okay. Now it's a Linux and other. It's a work of, you can say, teamwork. You can say. I will show how it's actually work by using the diagrams. For now, just understand it and remember that. Okay, so second one is the interception. It's happened at kernel level. Okay, the hook is the packet destined for a cluster IP like virtual IP enters the node, and the Linux kernel let filters framework work as a gatekeeper and it's intercept the packets. Okay, so the decision instead of standard routing, the kernel forces the packet to evaluate the specific IP table chains created by Kubernetes. And third one is the DNet, the switch. So the process of DNet is the like it performs IP table DNetting. Okay. So here it's transformed the original destinations like service cluster IPs and also the actual pod IP of destination. Okay. Like here, when packets are basically leave from pod A and want to go to pod B, that is basically sitting on different nodes. So how these packets will travel basically at first level it has information of only the pod networking. Okay, so now it's want to transfer by using the node network to, because it want to go to node B, so then it's basically encapsulate the node networking. Okay, so now you can think a layer, two layers of capsule. Inside the first capsule there is the information of like which pod we want to visit, and over that there is a second layer where we have the information like on which node we have to go. You can think like that. So what happened? The sender thinks it's talking to the service, the pod thinks it's receiving the direct request. Okay, so now both problem resolved due to the encapsulation. So fourth one is load balancing. So logic of load balancing is like if a service has multiple backend ports. Okay, so in Kubernetes it's also possible. Any service can have multiple backend nodes. So how it works? So it's basically uses backend ports multiple. It can have multiple ports. Okay, so it's here iptables basically uses the statistical approach to determine like for on which pod we have to send the traffic. So mechanism is like based on algorithm. Okay, it applies the random probability rule to chain. Okay, like for two ports the first rule has 50% chance to match. If it's fail, the second rule catches the remaining 50%. Okay, like in that manner. There are multiple algorithms is also there. So benefit of that is the provides good enough distribution without the overhead of the dedicated heavy load balancer. Okay. So now there are some more advanced concept of kube-proxy that uses the basically IPVS and eBPF. Okay, to solve the IP tables scaling issue. That way, like if you have 5,000 plus clusters, pods services, then we have the pods also thousands of pods. Okay, so then it will create a performance bottleneck. Okay, so for resolving that we use the IPVS. So basically what is IPVS? It's a basically internet protocol virtual server. It uses a hash table instead of list. Okay, So there in iptables we are using the list, but here it's using the hash table. Now if you know the hashing, then there is the time O1 complexity. Okay, so it's lookup time regardless of service count. Okay, and second one approach is the Cilium, like eBPF. Okay, basically it's implemented by using the Cilium. Okay, so it's completely bypasses the standard Linux networking stack for near native speed and advanced security. Okay, so it means your complete networking or implementation can be changed based on your choice of the CNI provider. Okay, so like person A can explain the Kubernetes networking in different manner, and person B can explain their Kubernetes networking in different manner, and person C can explain their Kubernetes networking in different manner. Okay, so you have to understand the basic concept. Yeah, that is possible. Why? Because if they will change their CNI provider and their CNI plugin, then obviously their networking implementation will change in Kubernetes. Okay, so one important thing is the discovery, service discovery. So how this work? It's basically work by using the core DNS. So how do pods find a service IPs? So basically it uses a core DNS, a watcher that track the Kubernetes APIs. Okay, so how this core DNS will also work? It's basically uses the etcd database, which is the basically key value database. Okay, so first we will study in one by one manner, then at last you will get the whole idea, like how everything work together. Okay, right now just we are talking part wise, but in real time all things work simultaneously as a system. Okay, to get work done. So naming convention like here, like myservices.mynamespace.sbc.cluster.local. Here you can also take your domain name. Okay, this is the just the default one. Okay, so workflow will look like pod ask for a DNS, pod ask from the core DNS, DNS returns the cluster IP, and it's sent to kube-proxy to route to pod IP. Okay, so the most important thing in Kubernetes is the, if you know about from where traffic should come and from Kubernetes where traffic should go, then you should have to remember two concepts. First one is for incoming traffic you need to know ingress, and for outgoing traffic you need to know about the egress. Okay, so let's talk about the ingress here. So if cluster IP, we know that if cluster IP is internal, then how do users reach us? Okay, so intuitively we know that cluster IP is the internal. So how do users reach us? So answer is by using ingress. So layer 7, it's work on layer 7. Okay, so it operates at the HTTP or HTTPS level. As we know, layer 7 work there. So main feature of the ingress is like SSL termination, path-based routing. Like here at separate path, we can send network traffic. Okay, we can segregate traffic, and the host-based routing. These are the main features. So here, how we can implement the ingress controller? So basically we use the nginx, hproxy, traffic to fulfill the ingress roles. Okay, so let's understand one more thing that is currently being used by enterprise. That is the gateway API. So it's basically a successor of ingress. Why? Because ingress was too simple for complex enterprise. So here in gateway API it's basically a role oriented. Okay, so it's basically separates infrastructure like gateway class from the application HTTP routes. Okay, so its capability is it has built-in support for header manipulation, traffic splitting, canary due to that canary deployments work, and it has multiple enterprise grade protocol support that we lack in basic ingress. So let's understand the difference between the ingress and gateway API. So here on the basis of feature we have made the comparison. Okay, so first one is API architecture. In ingress API, that one is basically a monolithic, based on monolithic architecture, one resource for host, path and TLS. But gateway API has composite architecture. It's split into gateway classes, gateway and routes. And here let's talk about user roles features. So it's a basically single user, development and admin share the same IML. But here gateway API is role oriented, separates platform, network and app teams. Okay, so here it's basically more enterprise oriented. Gateway API is more enterprise oriented because role or separate role is required in enterprise. It's not only negotiable. Okay, so traffic splitting, it's require vendor specific annotation, it's have native support built-in well field or can be a blue-green deployment, and header tuning requires vendor specific annotation and native supports built-in filters for header manipulation. Okay, so here we have in ingress, it's basically support the HTTP and HTTPS only, but here we gateway API support natively HTTPS, gRPC, TCP, UDP and TLS routes and also more. It's basically extensible. Okay, so in cross namespaces, ingress API has very limited or difficult features. Okay, usually confined to one namespace, whereas it support the gateway API support the cross namespaces, like its root can attach to gateways in other namespaces too, and portability is very low in ingress, whereas it's high inside the API. Okay, so let's move further. So let's understand about the network policy. What are the basic network policy? It's basically you can think about a firewall. You know that firewall, here you write rules. So like which host can communicate from which host on which port. Okay, so the same we can define in network policies, like which ports can communicate from which port on by using which service by which on which port. Okay, so we all can define inside the network policy. So by default Kubernetes is allow all network policy provider. Okay, so by default within a single host all port can communicate to all other ports on every port. It means it's allow all. So by using network policy we can implement some rules, like we at selector levels we can apply rules to port based on the levels, like app, database. Okay, like on which port it should communicate. Okay, and here it's allow only rule. One more thing, here it's allow only. It means the things when we implement some network policy, then suddenly it's become the allow only. Okay, it means when we allow that port or service, then only that service or port can communicate to others based on our defined level selectors. Okay, so it's basically defined ingress who can talk to me and egress who I can talk to. Okay, and it requires CNI that supports them, Calico, Cilium. Okay, like Flannel does not support the network policies. Okay, so that's why I previously told you, based on your requirement you have to choose the CNI. For that you have to also do the brainstorming if you are going to implement the Kubernetes networking, like what exactly you want to achieve in your cluster and what is your requirement of application or your company, you can simply say that, or your team. Based on that you have to choose the CNI because everything will change. Okay, so service mesh is basically used for layer 7 connectivity. When basic networking is not enough, we use a service mesh like Istio, Linkerd. Okay, it's basically based on sidecar pattern, like a proxy or invoice sits inside every pod. Okay, it means a agent will sit on every pod, or Istio agent will sit on every pod and work for providing the advanced networking features. Okay, so it's basically uses MTLS, automatic encryption between all services. Okay, so observability, so it's very useful for observability because it can trace and give the matrices for every single request without changing the application code. Okay, so in enterprise it's basically always used. Okay, but in Kubernetes it's just an optional thing, but in enterprise it's not optional, it's a mandatory to maintain the basically compliance with the compliance authority or regulators, you can say. Okay, so how we can basically troubleshoot the stack? So we have to think, always think in outside in manner. So we have to remember that outside in troubleshooting framework. Okay, so like we here troubleshoot in layered approach. Like in layer 1 we can think like the external perimeter. First of all, it's reaching us or not. Okay, like the client can test from the user's location. He can take the actions like he can ping, trace route, NS lookup, execute event, because there might be the issue. It can be issue with the external firewall. Might be some external DNS is not working. Okay, so there are multiple things. Okay, so always follow this approach, in this thing. Okay, so then we go into layer 2, like the cluster level entry, like gateways. We will check API gateways, ingress rules. Okay, from there we can, if we have the ingress, then we can use the nginx. If you have the gateway API, then we can also check the more things. Okay, and after that we can also check the routes and the certificates. That is the very important in today's world, because it's usually when certificate expires you are not able to open it. And then we go into one more deep layer, and here we check the basically endpoints. That is very critical, where most of the internal failures happen. Okay, so action is like we can check the kubectl gets endpoints and then service name logic. If endpoints are empty, the network is fine, but the pods have failed, the readiness proofs. Okay, so here we can also check the selectors, and also we can check the node level routing tables. Okay, so last one thing is we can check at node or pod or application level. Okay, so here we can check the logs, pods of it means here we can check the logs related to node, pod. Okay, we can also log in inside our container and our pod to check like everything is fine or not. At last moment we can also track like if any changes is done in recently in our infrastructure. Okay, at any layer that might cause the ripple effect. Okay, so let's understand it here more deep. So this is the basically a deep drive architecture. Here we have 6 node cluster. Basically it have 3 control plane and 3 data plane. Okay, like here external users come, like this is the external user. It's basically go through ingress as we already discussed. So in enterprise environment we have high availability external load balancers. Okay, that work on basically layer 4 or layer 7 load balancers. Like it might be the cloud provider load balancer or F5 in our in-house load balancers that basically send traffic to the ingress controller. Okay, after that traffic come to the ingress controller. Now here it can set at this level. These load balancers have path-based routing. Can also they basically send, if they can check, they can analyze whether this is a request for the this worker node, or you can say for any container, or it's a request or API call for the admin access. Okay, so if request for the admin access, then it can directly route to the master nodes, okay, to leader. Like here, if it's a 3 nodes, then there will be the must single leader here, okay. Suppose if leader will be the master node 1, then all decision will taken care by the master node 1, okay. So they basically communicate. Here you can see that their traffic is going. This is the etcd cluster traffic, okay. So it's basically maintaining the quorum. Why we always take the nodes in like in the form of 3, 5, 7, okay. Why? Because we have to maintain the high quorum, okay. So that's why, like here, if one node will fail, then here also we have the 2 master nodes, so we have the maximum quorum, okay. It means more than 50% of quorum, okay. So actually here on every node failure there is a voting system or election, you can say that. Like when system fails, the leader will be elected, and the same leader will work till what time? Till the next system failure, okay. Till the next master node failure, you can say, okay. So here, like, election will only happen when any master node will fail, okay, or any failure will happen in those nodes, okay. So here it's basically send some traffic, like leader send traffic to their subordinates, like, yes, are you alive? Are you alive? Then they can first either respond. If they will be alive, then they will firstly respond, otherwise they will send back, or simply they will not provide any response. Then here leader can think that the node is currently not alive, and their leader can evict that node, okay. Now you have to further check that, like what happened to that master node. On the basis of that, you can take the decision. Let's go in this direction. So here, like, it's here layer 7 routing logic Kubernetes services. Like here our first traffic will hit to the ingress controller, okay. That has also the layer 7 routing logic, okay. It means it can also further segregate the traffics, like it might send traffic based on to the certain path, like there might be some services that is for, there might be some request that is for any specific port. So based on that, he can send the traffic to that port only, okay. So here L7 routing logic will be here, okay. And here Kubernetes will talk with the Kubernetes cluster IP for the getting the IP. So basically now it sends request to kube-proxy, and then kube-proxy provide the endpoints, and then endpoints provide the actual pod IP there, okay. So then here you can see that kubelet and kube-proxy are basically working with CNI plugin. It's not like traffic is going in that manner, okay. But they are basically working with here inside the pod. When you get the pod IP, then it's basically our network traffic reaches inside the pod, okay. So here it's basically working with the kubelet and kube-proxy and the CNI plugin to pass the traffic to inside the container, okay. So this is the thing, like here how now it reaches to pod A, and now if pod A want to communicate with the pod B, then how it's happened, then it's also go with the CNI plugin, okay. So here kube-proxy, kubelet all work with the Linux kernel, okay. So all traffic here, you cannot simply think like this is flowing in the like same manner here just illustrated, okay. Multiple things are working concurrently. This is just for demo, okay, to conceptualize things, but this is also not 100% correct here. You have to think about that, because all things work concurrently. Multiple things here also. Kernel, we will see how kernel namespaces interact, okay. So in that manner, this complete traffic is working. Now after that, it basically send to egress to send the response, okay. So that's it for this. One more thing we will understand by using some other diagrams too. Simple diagrams basically, like here, there you can get confused. like if you have two pod basically. Okay, so let's understand the first between the pod. If pod A want to communicate with this pod B, okay, so this is inside the same pod. Okay, so this is basically here it's node A, it's node B. Let me give a name. These are the worker node. Let's suppose worker node A. Okay, so this is worker node B. Okay, so when traffic has to go from pod A to pod B, then what will happen? There will be some virtual interface, virtual veth is connected with the every pod. Okay, that I already told you. So basically there are two things. One side will be connected from the this Linux kernel. Okay, you can see that CNI bridge. Basically this is the CNI bridge, which that is basically inside the Linux kernel namespace. It's okay. So it send traffic to this virtual veth. Okay, you can see that, and then by using CNI bridge, that traffic will simply route it to the pod B. Okay, it means everything will happen at CNI bridge level, and this traffic has not go outside this node A. Okay, so now just its communication will happen in that manner, like from pod A, here it's come here, then here, then here, then here, then here. Okay, now if pod B want to send the response, then they can also send in that manner. Okay, so here we can, based on our CNI, we can implement the basically access policy here. Okay, you can think that, so that pod here right now pod A is freely communicating with pod B on any port or by using any service. Okay, but when we implement the policies, then allowed only allowed ports on which it's basically allowed can communicate. Pod A can communicate with pod B, and pod B can communicate to pod A. Okay, so here right now let's we can have a scenario like pod A traffic want to reach to the pod C. Now how traffic will move? Now first its traffic goes to this veth interface, then it goes to the CNI bridge. In some cases here Linux kernel, it directly uses the Linux kernel routes, okay, to send the traffic to pod C. Okay, but here most of the CNI provider uses the CNI bridge to communicate. Okay, so here traffic will goes like it's go to vth, then CNI bridge, and by using the Linux kernel, it's basically passes here to vnic. Okay, and by using here, it's basically go into this main LAN overlay. Basically this is the overlay or underlay network. Okay, here you can think about this is the, let me just write here so that you can just for your understanding, it's it may be overlay. If it will be virtual, then it will be overlay, otherwise it can be underlay network. Okay, so here by using overlay or underlay network, it's basically reaches to this vnic or nic, and enters traffic enter in the Linux kernel. Here there is already CNI bridge is here, and then it's by using this CNI bridge, it reaches to this veth interface, then inside the pod C. Okay, so here also there is a IP, some IP will be assigned here, so those IP will be managed by the CNI plugin itself. Okay, so this CNI plugin is responsible for here, let me add one more box. CNI plugin is responsible Okay, it's basically a CNI plugin also work with the which kubelet kube-proxy and also with the Linux kernel. Okay, so this is not the single person task. Basically multiple things are happening, okay, here. Okay, so for that now you understand that. Let me theoretically I will show you one more thing so that you have better understanding. You should not have any confusion. Like to understand how a packet travels from node A, pod A, node 1 to pod C, node 2. We have to look at the Russian doll effect of network encapsulation. So like in a standard Kubernetes cluster using an overlay network like VXLAN, the packet is wrapped multiple times to traverse the physical network. Okay, so let's take an example, a scenario like our source pod A has some IP 10.244.1.5 on node 1, and also node 1 has IP of this 192.168.1.10. okay, and pod C has this IP 10.244.2.10 on node 2, and node 2 has IP 192.168.1.20. Now how everything will happen? So I have divided it into 4 stages. So on stage 1 what will happen? So it's basically at the inner payload inside the pod namespace. What will happen? The application in pod A generates data like an HTTP GET request. Okay, so what application do? Application basically inside the pod namespace, it's basically generate HTTP GET request. Okay, now the pod's networking stack creates the initial IP packet with the source IP this pod A and the destination IP of pod C. Okay, now here nothing is like as I already explained the encapsulation, how encapsulation happen. Now just we are going with the example, real time example. Okay, so what actually happened? So now interface traffic leave by ETH0, okay, is one of the half part of veth pair. Like I have already gave you an example, like you can think like there is a veth as a wire, then the one side will be inside the pod and other side will be the inside the node or host, you can say. Okay, so now it leaves the veth0, suppose, then where it basically goes? It goes into the root namespace or the node bridge namespace, okay, inside the Linux kernel. Okay, the packet arrives the other end of the veth pair on node 1. The node 1 has the routing table. It sees that 10.244.210 is not the local IP address. Okay, it's basically not the local IP address because we have IP address range of 192.168. But currently it's asking for 10.244.2. What I will do? Now it hands over the packet to the CNI. Okay, now CNI come in picture. Okay, that has already implemented this networking. So our CLI should have all the information. Okay, so now the stage 3 begins, the encapsulation, the magic of VXLAN. If you know that VLAN, then it's similar to VLAN, just with some extended features. Okay, its name is virtual extensible LAN. So since the destination pod is on another node, the CNI must hide the pod packet so the physical network can route it. Okay, this is where VXLAN encapsulation happens. So outer UDP headers, the CNI wraps the original packet in a UDP datagram. Usually port 4789 is used for that. But if you are a CNI developer, then you can change, and also it can change as per your CNI plugin implementation. Okay, so there is no hard rule. You have to think that. You have to just conceptualize the things. Now VXLAN headers come into picture. It's add a VNI, VXLAN network identifier. So the receiving nodes know which virtual networks this belong to. This is just like a VLAN ID. Okay, so now outer IP headers, the envelope. Okay, so now it has the source IP 192.168.1.10, that is the physical node 1 IP, and it might be also physical, means that is node 1's main IP. So if node 1 is the virtual machine, then it's definitely its IP will be assigned on the virtual interface. But here you have to conceptualize that there is the physical node IP. Okay. So destination IP is like 192.168.1.20. It's a physical node 2 IP. Now we have the IP address of node 2. Now our packet can reach how? By using the routes, Linux routes. It's basically underlying, it's using the Linux technology, everything. Okay, so if you have the good idea of Linux, then you should not have any confusion to understand all these concepts. If you don't know the basic Linux networking, then I am damn sure you are in trouble and you are horribly not able to understand that concepts. Okay, so first go, if you are beginner to Linux, then go to the my Linux RHL9 networking series so that you can better understand this Kubernetes networking. Okay, so now we have the node 1, node 2 IP. So now outer MAC address. Okay, so the MAC address of the physical NIC on node 1. Okay, it's also if a virtual NIC, then we are also have a MAC address. Okay, so don't go into that. Just think it's a NIC. Okay, physical or virtual. Here just I have taken example of physical NIC. Okay, so here it's a physical NIC in node 1 and node 2. So are the next hop gateway. So now the stage 4, the transit and decapsulation. Like we have encapsulated, we have make a capsule of 2 layer. So the wire, the physical switches only see traffic between node 1 and node 2. Okay, the most important thing. Now the physical or virtual switches that are being used for the node communication is only able to see the node 1 and node 2 IP and MAC addresses. Okay, so they have no idea of pod A or pod C exist. This is the most important thing. They have no idea at this level. So when it's arrived to node 2, the kernel on node 2 received the UDP packet on port 4789. It sees the VXLAN header and realize that it's an internal cluster packet based on the specification of that packet. When this packet will be received on node 2, okay, so it sees the VXLAN header is used there. Okay, now he think, because he have knowledge, now he think like something inside that packet, and mostly it has some internal cluster packet. Okay, so now the strap down, the kernel strips of the outer MAC, outer IP and VXLAN headers. Okay, now it's delivered the original inner packet source to destination is now exposed. Okay, now source 10.244.15 and destination 10.244.210 is now exposed because we have just broken or uncovered the first layer of capsule. Now the data inside that has shown and exposed. Now node 2 looks at this local bridge and find the VETH pair of port C, and now it's basically hand over to that VETH, virtual Ethernet pair, that is outside of node or host, you can say. Now yes, that is the one side of where now that traffic is absolutely it goes to the pod. Okay, that has IP 10.244.2.10. Okay, so now in that manner this all thing will happen. You can just summarize the package structure in that manner, like there are layers and the basis of layer, like outer Ethernet layers have some hardware MAC, like node 1 has some MAC, node 2 has some MAC. Outer, like node 1 has some IP, node 2 has some IP. Okay, outer UDP protocol support by using the VXLAN 4789 it's communicating. Now it's some, you can think VXLAN header as a VLAN header. Okay, so like there might be some number 4096, okay, or anything based on your VXLAN choice. Yes, who is making this choice? The C and I plugin provider. Okay, so always remember who is the main hero, you can say. VXLAN provider, because he is the complete network stack implementer. Okay, so now inner Ethernet come into picture. That has some virtual MACs, like it's a pod MAC. Okay, so here, and now inner IP will be exposed there when encapsulation and decapsulation will happen. Okay, now it's know where you have to route that. Alright, okay, so in that manner it's basically communicate. Okay, so most of the CNI communicate in that manner. At some CNI, direct its traffic goes to the Linux routing table, and Linux route table basically directly can route to the pod C. Okay, but also there this encapsulation concept will come in picture. Okay, so that's it. In this video we will basically see practically how all these things work behind the scene in next video. So thanks for watching this video. Have a good day. So in the next video we can expect practical of this, and also in next chapter we will learn the storage part of the Kubernetes. Okay, so thanks for watching this video once again.